Hello, boys and girls. I'm going to do a little overview of what we're doing in class today and then continue on with the notes as well. Kind of do it in two parts. First off, I'd like to apologize for the poor audio quality. I'm recording this on my iPad, currently experiencing a power outage where I live and no word as to when it's going to be done. So went back to school and I'm working off of an iPad instead of a home computer. But won't let that stop me from getting some stuff posted for you. So we were talking in class about electric force and how that was based off of electric charge. And we started off by doing kind of the simple things of saying we can have attractive or repulsive forces. Opposite charges attract, so electrons and protons will have negative and positive charges respectively, and so they'll attract each other, but if they're like charges, like two protons, two positives, they will repel. And I said over here that the amount of force that they will experience is going to be dependent upon the amount of charge and the distance between them. And didn't really draw a diagram for that, and I think it would be something that's a good idea to go ahead and create. So we're not going to get into electric fields and how to draw all that, but I'll use a little bit of that to try to demonstrate what's going on with the idea of distance changing. So first off, we're looking at this equation, Coulomb's law. And Coulomb's law is kind of a beast to look at and try to make sense of, but we got two things that are important here. We've got that there's the quantities of charge, Q1 and Q2, and we've got the distance between them, which is d. And if the amount of charge were to go up, then if either of them go up, even if it's a little bit, you're going to get an increase in the numerator of that problem, so you'd get more force. But if you wanted to get more force by having the distance change, if you didn't have the quantities of charge change, how would you manipulate the position of the two objects in order to get a larger force? Well, since the distance is in the denominator, if you want your whole problem to get bigger, you need your denominator to get smaller. So you got to bring the objects close together. So here's where drawing a little picture I think is going to be helpful. Let's imagine that we've got positive charge right here, and we'll go ahead and do a negative charge right here. If we envision the ability for these charges to exert forces as lines extending out, this is what we draw as electric fields. And I'll draw some lines going out in all directions like this. Well, not all directions because there's an infinite number of directions, but I'll draw 8 lines going out like so. For those of you that are fans of the Red Hot Chili Peppers, you might recognize this sort of a symbol. In fact, I'll go ahead and do 2 positive signs here. And both of these charges will have a similar sort of electric field around them. Lines that represent the ability to exert electric force. And as these two sets of lines interact, they're going to produce the repulsion. They're going to say, oh, I don't want to be near this other charge, I want to get away. These lines don't want to overlap, they can't. But if we just treat one of them at a time for right now, if we just look at this one charge, if we were to extend those lines infinite distances out, like so, if I were to get really, really close, and I don't know, say draw a loop, and maybe I should draw some more lines here. Let's draw some more lines. Try to keep it even, but let's say I had all these lines of electric force going out. If I draw a loop, and I draw it out of just some sort of pink marker here or something, and I've got drawn about that big, if I'm really, really close, and this loop represents the interaction level of a particle, you can see that it's encapsulating, let's see, there's 1, 2, 3, 4, 5 lines of electric force that are stuck inside of this loop. And that's with it being a particular distance away, like center to center. If I were to take that loop and move it further away, let's say to, I don't know, just about double or the distance or so, by moving it out that far, that's more like 2.5 or 3 times the distance, I go from having 5 lines going through my loop to just barely having 3 lines. So if you think of this as rays of light that you're catching with your eyeball, or sound going into your ear, or electric force intensity hitting you, in this area right here, I'm getting less interaction with the field produced by that positive charge. And if I were to move even further out, at some point, I'm getting like 1 line. And if I were to move out really, really far, and of course there's more lines of force than just that. If I'm off a no man's land here, I get nothing. So the further out you go, the less interaction you have with the field lines that are coming off of the charge. Less interaction is going to mean less force. If you go closer in, you're going to get more interaction with the field lines, you're going to get more force. So that's why there's this inverse relationship between distance and force. Now it's specifically an inverse square relationship, because as you increase the distance, you decrease the force. That's an inverse relationship. One gets bigger, one gets smaller. But the square idea doesn't come from anything actually being square. It has to do with the power of 2. And if we go back to this little sketch drawing thing I have here, unfortunately I changed that pink to blue by mistake. If I go back to this drawing, oops, I'm not thinking of this as a line. This is a surface. It's a hoop, and a hoop has a surface area. So the area of this, I'm sorry, the thing keeps screwing up on me there. That has an area which is proportional to a radius squared. And if I take that thing and I move it out here, well, I'm covering a very small area compared to what, and I'll be careful here, originally we were covering all of those things. Well, as they go out, they're covering a huge area, and I'm just capturing a little teeny bit of it. So this is where that sort of a cone of light coming out from a light source gets weaker and weaker the further out you go, because your eyeball's catching less of it. It's spread out over a bigger area. Now this looks like a complete mess, but hopefully that idea gets across. So when we go back over to here and we talk about that inverse square relationship, we did an example number 1. And we said, what would happen if you were to take the distance between two charged particles and double it? Well, everybody said that it should decrease. The force should decrease because you're further away. But the exact mechanics of it were a little difficult. So we want to get across that idea of the inverse square relationship here. If you move twice as far out, you have 4 times the area that would be encapsulated by the electric field, but you're still looking at just a teeny little bit of it. So you're looking at a fraction of it, so we have to invert it. So let's take a look at the idea of an inverse square to try to solve this. By changing the distance between two charges, we're going to say that whatever change is made to the distance, change of the d, you take the change in distance invert it, then square it. So 3 steps. So if I were to take the distance and multiply it by 2, I would take 2 times the distance. But if I wanted to invert that, that would be 1 over 2. And if I square 1 over 2, I get 1 over 4. So inverse square. Invert your change and square it. Let's see what would happen if we were to do the opposite. If we were going to take that surface area that we have here and move it closer in, decreasing the distance. What if you had, I don't know, we decrease it to 1/5, all right? So the change in d, let's say it's 1/5. Let's say we go from 5 meters to 1 meter. We invert it. Now, a reminder, if you get a smaller distance, you should get bigger force. So inverting it, we'd have 5, or 5 over 1, but we'll just put 5. And then if we square it, we'd have 25. So 1/5 the distance gives you 25 times the force. You're bringing in it close, and you're going to get a lot more force because of that. Okay, that's going to be it for this first part of the notes rehashing. Hopefully this has helped you understand that concept just a little bit better. It's one of those things, like I said, that you get it and then you think, oh, how could anybody be so stupid not to get this? But it takes a bit of time. So hopefully that helped. See you in the next video.